Welcome back, learners. Ready for another deep dive?
Always ready.
Today, we're tackling Poisson genericity in numeration systems.
Oh, yeah, that's a good one.
It's based on this paper by Alvarez, Becher, Cesaratto, Mereb, Peres, and Weiss. Poisson genericity in numeration systems with exponentially mixing probabilities.
Definitely a mouthful.
But don't let the title scare you off. The core idea is really quite elegant. It's all about how these seemingly random patterns in number sequences can actually follow predictable distributions.
Exactly. The paper goes deep into how these occurrences, like specific sequences of digits or something in a numbers expansion, well, they can show patterns we see in probability all the time, the Poisson distribution.
Yeah, so before we go too far, can we just quickly recap what the Poisson distribution is?
Sure. Imagine you're at a bus stop and the buses arrive randomly. The Poisson distribution tells you the probability of a certain number of buses arriving within a given time.
So like you might have some times where a bunch of buses arrive close together and other times where there's nothing for ages.
Exactly. It's often used to model events that happen independently at a constant average rate.
And what's fascinating is that this seemingly simple distribution pops up in all sorts of unexpected places. Like this paper shows it's even in abstract number sequences.
Right.
So how does this paper connect the Poisson distribution to these number sequences? I know it has something to do with continued fractions, right?
Yeah, that's a great starting point.
Yeah.
Let's say you have a real number, any real number. You can express it as a continued fraction, which is basically a whole number plus a fraction where that fraction's denominator is a whole number plus a fraction and so on.
Like those Russian nesting dolls, but with numbers instead of dolls.
Perfect analogy.
So what this paper shows is that the sequence of whole numbers in these continued fraction expansions, they exhibit this Poisson-like randomness for almost all real numbers.
Yeah.
So we're not talking about just any random sequence, but the specific sequence of numbers that make up a continued fraction representation of a real number.
Precisely. And the randomness comes in when we look at the frequency of specific sequences of these numbers and how that changes as those sequences get longer. What they found is that this frequency follows a Poisson distribution.
So essentially, the paper argues that for most real numbers, their continued fraction fingerprint displays this Poisson-like randomness.
Exactly. It's a pretty amazing connection between a seemingly simple probability distribution and the intricate structure of real numbers.
Okay, that's starting to make sense. But to really grasp this concept, I think we need to get to the heart of the paper, Poisson genericity.
Definitely.
What exactly do we mean by Poisson genericity?
Imagine you're watching cars passing a point on a highway. If the arrivals are truly random, the number of cars passing in a fixed time should follow a Poisson distribution. So Poisson genericity means that the occurrences of specific patterns, or you could say blocks, of symbols within a sequence, well, they become increasingly Poisson distributed as the block length increases.
So it's like we're looking for patterns within a sequence. And the more complex the pattern, the more its occurrences resemble this random but predictable Poisson distribution.
Exactly. And the paper focuses on proving this genericity in systems governed by what we call exponentially mixing probability measures.
Okay, now we're getting to the more technical stuff. Can you break down what an exponentially mixing probability measure is and why it's important?
Imagine you're mixing ingredients for a cake. An exponentially mixing probability measure essentially means that as you mix that batter, events far apart in the sequence of ingredients become increasingly independent. It's a measure of how quickly the memory of the initial arrangement fades.
So in our number sequence world, it means that the occurrence of a specific pattern in one part of the sequence shouldn't really influence the occurrence of that same pattern much further down the line.
Exactly.
And this fading memory is key to having this Poisson-like randomness.
Yeah, it ensures that occurrences of our pattern become independent of each other, which is a defining characteristic of the Poisson distribution.
Right. So we have these abstract number sequences, and how those numbers are distributed is governed by this exponentially mixing property. And that sets the stage for this Poisson-like randomness to appear.
Exactly. But to analyze this randomness rigorously, we need to introduce another concept, point processes.
Point processes. Bring it on.
Think of a point process as a random collection of points. In this case, each point represents the occurrence of a specific pattern within our number sequence.
So we're mapping these abstract patterns to points in space and then analyzing how those points are distributed. I can see where the Poisson distribution might come into play.
Exactly. Poisson genericity is formally defined as the convergence of these point processes as the block length increases to a Poisson point process.
So the paper aims to prove that for systems with these exponentially mixing probability measures, the occurrences of patterns within the sequences will eventually behave like a Poisson point process. Truly random, but with a predictable overall distribution.
You've got it.
To tackle this proof, the paper uses two main approaches: annealed and quenched results. What's the difference between those two?
Think about baking a cake again. The annealed approach is like analyzing the average behavior across all possible cakes you could make with those ingredients. It's looking at the overall mixing process.
Okay, so it's like a global view. What about the quenched approach then?
That's like looking at a specific slice of the cake. You take one particular sequence and analyze its properties to see if it has that Poisson genericity.
So the annealed result sets the stage by showing the average behavior, while the quenched result zooms in on individual sequences to see if they follow suit.
Precisely. The paper starts with the annealed result establishing a limit theorem using the Chenstein method.
Wait, the Chenstein method.
Yeah.
Can you refresh our memory on what that is?
The Chenstein method is a tool in probability theory that lets you compare the distribution of a sum of dependent random variables to a Poisson distribution. In this case, it helps quantify how much the distribution of pattern occurrences deviates from a true Poisson distribution.
So it's like a measuring stick for how Poisson-like our pattern occurrences are.
Precisely. And the paper uses this method to show that the deviation shrinks as the pattern length grows and eventually converges to a true Poisson process.
So the longer and more complex the pattern, the closer its distribution gets to a perfect Poisson distribution. But how does the paper go from this average annealed view to the quenched perspective of individual sequences?
Well, that's where things get even more interesting. They introduce another powerful tool called concentration inequalities.
Concentration inequalities. Tell me more.
Essentially, a concentration inequality provides a bound on how much a random variable can deviate from its expected value. In our case, it tells us how much the pattern distribution in a specific sequence differs from the average Poisson-like behavior we got from the annealed result.
So it's saying, okay, we know the average behavior, but how much can individual sequences wiggle around that average?
Exactly. And the sharper the concentration inequality, the tighter those bounds are, and the more confident we can be that most individual sequences will indeed show that Poisson genericity.
This is fascinating stuff. We've gone from continued fractions to mixing measures to point processes, and now concentration inequalities. It feels like we're building this whole toolkit for understanding randomness in number sequences.
Yeah, you're right. And we've only just begun, ready to dig deeper into how the authors use these tools.
Absolutely. Let's get into the nitty-gritty math.
Okay, great. Let's start by looking at how the paper sets up a framework for analyzing these point processes.
Sounds good. Let's do it.
So the paper sets up this framework where they analyze the distribution of a specific random measure. It's denoted as ws. This measure basically represents the number of times a specific pattern ws appears within a set S of scaled positions along our number sequence X.
So we're not just looking at whether a pattern shows up, but also where it shows up in the sequence and how many times.
Exactly. And the scaling of positions is important because we're looking at how this distribution changes as the length of the pattern W, which we'll call K, grows. Remember, we're trying to show that as K increases, the occurrences of W start resembling a Poisson point process.
Yeah, okay, that makes sense. So Chemley's WS is giving us a detailed picture of how this pattern WE is spread out across our sequence X, but how do we actually analyze this measure, especially when we're dealing with these exponentially mixing probability measures?
That's where some serious probability theory comes in. The authors use a series of lemmas to break down the expectation and variance of MIMK-LWSS, taking advantage of that exponentially mixing property.
Hold it, can you back up a bit? Why are the expectation and variance so important?
Well, think of it this way. The expectation gives us the average number of times we'd expect to see the pattern W within the set S. The variance tells us how much the actual number of occurrences might differ from that average. They're basically fundamental statistical properties that help us understand a random variable.
Right, so by looking at the expectation and variance of MIMK-LWSS, we're basically understanding how this pattern W is distributed along the sequence X.
Exactly, and that's where the exponentially mixing property becomes really important. Lemma 1 in the paper shows that the expected value of Mon-Kebby SS is essentially equal to the Lebesgue measure of the set S plus an extra term that disappears really quickly as the length of the word W
Okay,
increases.
hold on. Lebesgue measure. That sounds familiar from measure theory. Quick recap.
Sure, the Lebesgue measure is a way to assign a size to subsets of a space. For a simple interval on the real line, it's just the length of that interval. But it can be extended to more complex sets in higher dimensions, too.
So the Lebesgue measure of S basically tells us the size of the region
Yeah.
within the sequence X where we're looking for W.
Exactly. The fact that the expected value of Mereb is so closely related to the Lebesgue measure is pretty intuitive.
Huh.
A larger region means more chances for the pattern W to show up, so we expect to see it more often on average.
That makes sense. What about the variance, though? Does it also behave well with these exponentially mixing measures?
It does. Lemma 1 also shows that the variance of Griswes is equal to the Lebesgue measure of S plus a term that decays exponentially with the length of W, except for cases where W has a repeating internal pattern, or what the authors call a period.
So these periodic patterns make things a little more complicated. But even then, the variance still matches up with the Lebesgue measure as the pattern length gets bigger.
Yeah, exactly. Now, equipped with this understanding of the expectation and variance, the paper uses the Chenstein method to look deeper into the distribution of more fed SS.
Okay, time to break out the Chenstein method. Remind me again what this method is all about and how it helps us here.
The Chenstein method is a fantastic way to compare the distribution of a sum of potentially dependent random variables to a Poisson distribution. It provides a way to bound the difference between those two distributions, which is crucial for proving convergence.
So it tells us how far off the distribution of our pattern occurrences is from a true Poisson distribution.
Precisely. And the paper uses this method to prove lemma 4, which is key to the annealed part of the proof. This lemma shows that the total variation distance, a measure of how different two probability distributions are between the distribution of Mach WSS and a Poisson distribution with parameter equal to the Lebesgue measure of S, actually shrinks to 0 as k increases.
So the longer the pattern W we look for, the closer its distribution of occurrences gets to a perfect Poisson distribution. It's like the randomness gets more pure as the pattern gets more complex.
Exactly. And this convergence, as the paper shows, is pretty subtle. It happens in the product space of sequences and patterns. This is a key point because it shows how the structure of the sequence X and the specific patterns W are connected.
That's interesting. It's not just about the patterns themselves, but how they fit within the larger sequence.
Exactly. Now, this convergence in lemma 4 is a big step, but it's still just dealing with the average or annealed behavior. How do we go from this to those quenched results about individual sequences? Well, that's where those concentration inequalities we mentioned come in.
Okay, time to bring on the concentration inequalities. Remind us what they are and how they bridge this gap between the average and the individual.
A concentration inequality lets us put a limit on how much a random variable can deviate from its expected value. It helps us see how much the pattern distribution in a specific sequence might differ from that average Poisson-like behavior we found with the annealed result.
So it's like controlling the wiggle room for individual sequences around the average. And the stronger the inequality, the tighter the control rate.
Right. The paper uses a concentration inequality specifically for functions with infinitely many variables. This is important because our sequences could be infinitely long.
Makes sense. We need a tool powerful enough to handle those potential infinities. But not just any function will do right. There's some special property these functions need for the concentration inequality to work.
You got it. The paper shows that the function that measures the proportion of patterns in a sequence, well, it satisfies something called the Lipschitz condition.
Lipschitz condition. I kind of remember that from calculus.
Yeah.
It has to do with how much a function's output can change based on a change in its input, right?
Exactly. Simply put, a function is Lipschitz continuous if there's a limit to how steeply it can change. Small input changes lead to proportionally small output changes.
So here the Lipschitz condition means that small changes in the sequence X won't cause huge unpredictable swings in the pattern distribution.
Precisely. This smoothness property, combined with the concentration inequality, helps the paper prove lemma 9. It establishes two important concentration results.
2. What's the difference?
The first part of lemma 9 looks at the average number of times a pattern shows up in a sequence. It shows that this average doesn't stray too far from its expected value, which we know is tied to the Lebesgue measure of the region we're looking at.
So individual sequences generally stay close to the average when it comes to the overall pattern count. What about the second part of lemma 9?
That one's even more important for our goal of showing Poisson genericity. It shows that the proportion of sequences that have a certain number of pattern occurrences, well, that doesn't go too far from its expected value, which we know converges to the Poisson probability from the annealed result.
So it directly connects the behavior of individual sequences to that Poisson distribution we established in the average case.
Exactly. This connection leads to lemma 10, which establishes the quenched result. It uses Kahlenberg's theorem again.
Kahlenberg's theorem is back. Remind us what this theorem is all about and how it helps us with the quenched result.
Kahlenberg's theorem gives us conditions for when a sequence of point processes converges to a Poisson point process. The paper shows that for almost all sequences, these conditions are met thanks to those concentration results from lemma 9 and the properties we've seen so far.
So it's like we've climbed this math mountain step by step, and now we're at the peak, looking at the view of Poisson genericity in almost all these sequences.
A great analogy. We've shown that even though those patterns might look random at first, there's a deeper, more predictable structure at work governed by the Poisson distribution.
It's really amazing how these different areas of math, number theory, probability measure theory all come together to find this hidden order in the apparent chaos.
Absolutely. And it's not just the results themselves, but the journey we take to get there, the tools we use, the new perspectives we gain.
Speaking of tools, the paper mentions mixing coefficients organized into a matrix called GAM. Can you explain those a bit and how they fit in?
Sure. Let's look at the mechanics of mixing and how these coefficients help with the proof. So these mixing coefficients, they're denoted as A, and they basically measure how dependent events are at different spots in our sequence. Remember that exponentially mixing property? Well, these coefficients quantify how quickly that memory fades as you move further apart in the sequence.
Right, so the further apart two events are, the less they should influence each other. Like ripples in a pond, they fade out as they spread.
Exactly. The paper organizes these mixing coefficients into a matrix denoted by element. It captures the overall mixing behavior of the system, which lets us use some cool techniques from linear algebra and functional analysis.
Sounds like some serious math is coming up. How do these mixing coefficients in the element 6 help prove Poisson genericity?
They're crucial for bounding something called the Zuma-Hofting coefficients. These coefficients help us control how much certain functions can deviate from their expected values, and they tie directly into those concentration inequalities we talked about.
So by bounding these Zuma-Hofting coefficients, we're essentially taming those functions, making them more predictable and aligning them with that Poisson behavior we're looking for.
Exactly. Think of it this way. The Zuma-Hofting coefficients measure how sensitive a function is to changes in the input sequence. The smaller they are, the less the function's output will fluctuate.
Okay, so by carefully analyzing these mixing coefficients and bounding the Zuma-Hofting coefficients, the authors essentially create a solid link between the average behavior and what happens with individual sequences.
Exactly. It's this beautiful chain of reasoning, and each link strengthens the whole argument. What's even cooler is that the paper doesn't just stay in abstract theory. It gives concrete examples of numeration systems where these results actually apply.
That's great. So this isn't just some theoretical possibility. It applies to real ways of representing numbers.
Absolutely. The paper specifically mentions integer-base expansions, beta expansions, and those continued fractions we talked about earlier.
So this Poisson genericity is baked into how we represent numbers. It's like this hidden order within all the digits and fractions.
Precisely. And even beyond these specific results, the paper opens up a whole new area to explore. For instance, can we actually build specific sequences that are Poisson generic?
That's a great question. Instead of just proving that almost all sequences have this property, can we engineer sequences that have it on purpose?
Exactly. And that brings up even more questions. What if we use those specially designed sequences to create better random number generators or systems with very predictable behavior?
It's amazing how one paper can spark so many new questions. It really shows the power of math research.
I agree.
So there you have it, learners. We've explored the world of Poisson genericity, seen its implications for how we represent numbers, and learned about the awesome mathematical tools used to prove these results. It's a testament to how elegant and interconnected math is in our quest for finding patterns in the universe.
And remember, this is just the start. The world of math is huge and full of surprises. Who knows what other amazing connections are out there waiting to be found?
Keep those mathematical minds curious and those neurons firing. We'll see you on the next Deep Dive. Welcome back to the Deep Dive, where we plunge headfirst into some fascinating research.
Always exciting.
Today, we're going to tackle a paper that blends randomness and predictability in a way that might just bend your mathematical mind.
Oh, it's a heady mix, that's for sure.
The paper is called, get ready for it, Poisson Genericity in Numeration Systems with Exponentially Mixing Probabilities.
Got a mouthful.
Yeah, Alvarez, Becher, Cesaratto, Mereb, Peres, and Weiss. Quite a lineup.
Definitely.
Before we even get to the meat of their work, the title itself is hinting at some pretty high-level concepts.
You're not wrong. We've got Poisson distributions, which deal with the probability of certain events happening over a fixed interval. And then we're layering on numeration systems, ways of representing numbers, and this idea of mixing probabilities, which gets into how events influence each other over time.
Right, and smack dab in the middle of it all is genericity, which in this context means we're not talking about just a few special cases, but something that holds true for a vast majority of systems meeting certain criteria.
Exactly. The core question here is how often do specific patterns pop up within sequences generated by these numeration systems? And does that frequency align with what we'd expect from a purely random Poisson process?
Okay, so it's like asking, if we flip a coin 1,000,000 times, will the number of times we get, say, 5 heads in a row actually match the Poisson distribution's prediction?
Exactly.
But instead of coins, we're dealing with these more abstract mathematical systems.
A perfect analogy. And what's fascinating is that this paper builds upon earlier work by Rudnick, Peres, and Weiss, who tackled Poisson genericity in the realm of integer base expansions, think base 2, base 10, that sort of thing. They found that for almost every real number, its representation in these bases exhibits this Poisson-like behavior in terms of digit patterns.
So this new paper is taking that foundation and saying, hold on, this might be way more universal than just integer bases.
That's the crux of it. They posit that any system using a finite or countable set of symbols, imagine an alphabet, can exhibit this Poisson genericity, provided it adheres to certain probabilistic rules, namely this exponentially mixing probabilities bit from the title.
Okay, so let's unpack that a bit. Exponentially mixing probabilities sounds like a recipe for some serious mathematical chaos.
Not quite chaos, but certainly a lot of interdependence. Essentially, it means events within the sequence influence each other, but that influence decays exponentially as they get further apart. Imagine ripples in a pond. The closer you are to the initial splash, the stronger the wave. But further out, it diminishes rapidly.
So even though there are dependencies, they become less and less significant over time.
Precisely.
It's like saying today's weather might heavily influence tomorrow's, but a month from now, that impact is pretty much gone.
Precisely. And this property, along with a few other key assumptions they lay out, sets the stage for their exploration of Poisson genericity in these broader numeration systems.
So they're not just expanding the scope of where Poisson genericity might exist, they're also giving us a framework for analyzing these systems and predicting how patterns will emerge within them.
Exactly. They're creating a sort of unified theory of pattern distribution across a vast landscape of mathematical sequences. And this has huge implications, not just within pure mathematics, but potentially in fields like computer science, cryptography, even our understanding of physical phenomena that exhibit random yet structured behavior.
This is getting me fired up. But before we get lost in the wilds of all the potential applications, let's dig into the mathematical machinery they used to prove their claims. The paper mentions some pretty heavy-duty concepts: mixing, invariance, the Chenstein method.
Yes, these are powerful tools from the realm of probability theory and dynamical systems. Mixing, which we've touched upon, formalizes that idea of decaying dependence between events.
Right. The further apart the events, the weaker their influence on each other.
Right.
But what about this invariance concept? Is that related to symmetry or something?
In a way, yes. Invariance, in this context, means that the probability of a specific pattern occurring within a sequence doesn't depend on where you're looking within that sequence. It's like saying the odds of rolling a 6 on a die are the same, whether it's your first roll or your 100th.
So it's about a kind of statistical uniformity throughout the sequence.
Exactly. Now, the Chenstein method, that's a real workhorse in probability theory. It's a technique for approximating the distribution of a sum of dependent random variables. And in this case, it helps them demonstrate how closely the distribution of patterns within these sequences aligns with a true Poisson distribution.
Okay, I'm starting to get a sense of the toolkit they're using. But they don't just throw these concepts around. They actually divide their proof into two major parts, right? The annealed and the quenched results.
You've hit the nail on the head. The annealed result looks at the average behavior across all possible sequences generated by a given system. It's like saying if we were to generate 1,000,000 sequences using this set of rules, what's the average frequency of a particular pattern across all of them?
And then the quenched result zooms in on individual sequences, saying, hey, does this Poisson-like behavior hold true even when we look at a single specific sequence?
Precisely. And proving both is crucial because it shows that this Poisson genericity isn't just a statistical artifact of averaging things out. It's truly embedded in the structure of these sequences themselves.
Okay, I'm ready to roll up my sleeves and dive into the nitty-gritty of these proofs. Where do we even begin?
Well, their approach is quite elegant, building up from foundational propositions about convergence to a Poisson distribution, to analyzing the behavior of individual words within sequences, and then culminating in these powerful annealed and quenched results.
This is going to be a wild ride. But before we get too far ahead of ourselves, let's take a breath and come back for part 2, where we'll unpack the proof in more detail.
Get ready for some serious mathematical fireworks.
Welcome back to the deep dive. We're about to wade into the depths of a proof that's as intricate as it is insightful.
Intricate is an understatement.
Remember, our mission is to understand how lvarez and their team demonstrated this remarkable idea that in a vast array of numeration systems, the frequency of patterns within generated sequences often mirrors what we'd expect from pure randomness, the Poisson distribution.
Right, and to get there, they've laid out this two-pronged approach, the annealed result, which deals with the average behavior across all sequences, and then the quenched result, which zooms in on what happens for almost every individual sequence.
And they kick things off with a proposition that's like a blueprint for proving convergence to a Poisson distribution.
Yeah.
But we're not talking about single numbers here. They're dealing with these things called point processes.
Right. Think of a point process as a way to represent events happening at random points in time, or in our case, within a sequence. Instead of just a single value, we're tracking a collection of occurrences.
So it's like if we were flipping a coin, a point process would capture not just the overall number of heads, but the specific positions where those heads occurred.
Exactly. And this proposition lays out two key conditions that, if met, guarantee that a sequence of point processes will converge to a Poisson process.
Okay, sounds like a powerful tool to have in our arsenal. What are these conditions?
Well, the first one focuses on expected values. Remember, the expected value of a random variable is like its average outcome over many trials. So this condition says that the expected value of our point process, the average number of events occurring, has to be less than or equal to the expected value of a Poisson process.
So on average, our sequence shouldn't be throwing out more events than a truly random Poisson process would.
That's the gist of it. The second condition is a bit more nuanced. It deals with the probability of having 0 events within a particular interval of our sequence. This probability has to approach the probability of having 0 events in a corresponding Poisson process.
So it's not just about matching on the average number of events, but also on the likelihood of complete silence, so to speak.
Precisely. And these two conditions, seemingly simple, set the stage for the rest of their proof.
Okay, now the paper dives into this concept of contraction ratio, denoted by the Greek letter rho. What's the intuition behind that?
So the contraction ratio essentially quantifies how quickly the probability of observing a specific word within a sequence decreases as the length of that word grows. It captures this exponential decay in probabilities.
So if we have an alphabet of, say, 0 and 1, the probability of seeing the word 0, 1, 0, 1 is going to be much lower than the probability of seeing just 0, 1.
Exactly. And the contraction ratio controls how steep that drop-off is. Mathematically, they say that the measure of any word of length, k, denoted μw, is bounded by some constant times.
So as k, the length of the word increases, that cock term is going to shrink rapidly because Rhodes is between 0 and 1.
Precisely. It's like saying the longer our word gets, the exponentially less likely we are to stumble upon it within our sequence.
Now, on top of this contraction ratio, they also introduced the bounded distortion constant, denoted by r. What role does that play in taming this mathematical beast?
Well, the bounded distortion property ensures that even when we have 2 words appearing within a sequence, their combined probability doesn't go haywire. It keeps their joint occurrence somewhat in line with what we'd expect if they were completely independent.
So it prevents these crazy scenarios where two words, when they happen to appear together, become way more or way less likely than their individual probabilities would suggest.
Exactly. It's like a sanity check on the dependencies between words.
And this bounded distortion property seems closely related to that idea of mixing, where the influence of past events weakens as we move further down the sequence.
You're spot on. The bounded distortion property helps guarantee that some mixing holds. Without it, we could have these weird situations where two distant words, even though they're far apart, somehow exert a strong influence on each other.
So we've got our contraction ratio keeping those word probabilities in check, and our bounded distortion constant taming the dependencies between words. It's like setting up the rules of the game for these sequences.
A perfect analogy. And with these rules in place, they can start tackling the annealed result. They want to prove that if we average over all possible sequences generated by a given system, the number of times a specific word appears within a certain interval will, as that interval gets larger, converge to what we'd expect from a Poisson distribution.
Makes sense. But how do they actually go about proving that? It seems like a daunting task, considering the infinite possibilities for these sequences.
Well, they start by zeroing in on individual words, proving some helpful properties about their expected values and variances within a sequence. And this is where the concept of periods of a word comes into play.
Periods, like the punctuation mark. I'm intrigued, but also a bit confused.
Not quite that kind of period. In this context, the period of a word refers to the length of the shortest repeating subunit within that word. For example, the word banana has a period of 3 because ban repeats.
Okay, so a period indicates some internal repetition within the word. But how does that connect to our goal of proving Poisson convergence?
Well, they establish this clever link between the periods of a word and how its expected value and variance, those measures of its average behavior and spread, behave within a sequence.
So the internal structure of a word actually dictates how it behaves statistically within the larger sequence.
Exactly. They show that as the length of a word increases, the variance of how many times it shows up is basically controlled by the length of its periods.
So words with short periods, lots of internal repetition, might be a bit more wild in terms of their distribution, while words with long periods are more tame.
That's a great way to think about it. And this insight is crucial for their next step, using the Chenstein method to analyze the entire sequence.
Ah, the Chenstein method, our trusty tool for dealing with sums of dependent random variables. But how do we even apply that here? I mean, we're talking about the whole sequence now, not just individual words.
Well, they cleverly frame the total number of times a word occurs within a sequence as a sum of individual occurrences at different positions. Each position is like a little random variable. Either the word is there or it's not.
So it's like breaking down a complex problem into smaller, bite-sized pieces.
Exactly. And the beauty of the Chenstein method is that it allows us to handle those dependencies between the pieces. The fact that the presence of a word at one position might influence its presence at another position.
So even though our events aren't perfectly independent, we can still approximate their overall behavior using a Poisson distribution.
That's the magic of Chenstein. And to quantify how good this approximation is, they use something called total variation distance, denoted by DTV. It's essentially a way to measure how different two probability distributions are.
So if the total variation distance between our word count distribution and a true Poisson distribution is small, we're in good shape.
Exactly. And they prove a key lemma that establishes a bound on this total variation distance. This bound depends on, you guessed it, our old friends, the contraction ratio and the periods of the word.
So those core concepts we established earlier are coming back into play. It's like a beautiful mathematical tapestry with all these threads weaving together.
You're catching on. And this bound on the total variation distance is crucial because it shows that as the length of our word increases, the distance between its distribution and a true Poisson distribution shrinks.
So the longer our word, the closer its behavior gets to that ideal Poisson randomness. I'm starting to see how they're building up to this annealed result.
And that's essentially the heart of it. They've demonstrated that, on average, as word length grows, the distribution of word counts within these sequences beautifully converges to a Poisson distribution.
That's a pretty impressive feat. But remember, this is just the annealed part. We still need to tackle the quenched result, where we zoom in on individual sequences. I'm guessing that's where things get even more mathematically intense.
You could say that. We'll need to bring in some heavy-duty tools from probability theory, like concentration inequalities. Get ready for a wild ride in part 3.
Welcome back to the deep dive. We're on the final leg of our journey into the heart of Poisson genericity. We've explored the annealed result, which gave us this beautiful average picture of how patterns behave across a vast collection of sequences.
But now comes the real challenge, proving the quenched result, showing that this Poisson-like behavior isn't just a statistical quirk, but actually holds true for almost every individual sequence generated by these systems.
Right, because averages can be deceiving. If we just looked at average height, we might miss the fact that some populations have a few giants and lots of really short folks, while others are more evenly distributed.
Precisely. So to go from that average picture to statements about individual sequences, we need a powerful tool, concentration inequalities. These are like mathematical guarantees that tell us how tightly a random variable is concentrated around its expected value.
So if we know the average height of a population, a concentration inequality can give us an upper bound on how many people are likely to be, say, a foot taller or shorter than that average.
That's the idea. And in our case, lvarez and their team use concentration inequalities to show that for almost every sequence generated by these systems, the distribution of word counts will be close to the Poisson distribution we'd expect based on the annealed result.
But we're dealing with infinite sequences here. How do you even apply a concentration inequality to something infinite?
That's where the cleverness of their approach comes in. They start by considering finite segments of the sequence and proving a concentration inequality that holds for those segments. Then they ingeniously extend this result to the entire infinite sequence.
It's like building a bridge by first laying down sturdy individual bricks and then connecting them in a way that spans the entire chasm.
A perfect analogy. And the specific type of concentration inequality they use is particularly well suited for handling sequences with dependencies, which, as we've seen, is crucial in our context.
Now, I know we're going to have to get a bit technical here, but the paper mentions these Azuma-Hufting coefficients, emixing coefficients, and even a matrix denoted by the Greek letter delta. Can you help us decode this mathematical alphabet soup?
Of course. These are all tools from the realm of probability theory and measure theory that allow us to precisely quantify the dependencies within our sequences and then apply the concentration inequality.
So the Azuma-Hufting coefficients are essentially measuring the influence of individual events within a sequence on the overall outcome we're interested in.
Exactly. Imagine our coin flipping example. The Azuma-Hufting coefficients would help us quantify how much each individual flip contributes to the final count of heads.
Okay, so we're isolating the impact of each little event. And what about those emixing coefficients? I vaguely remember us talking about Bixing earlier, where events become more independent as they get further apart.
Right. Vaxing was that general concept of decaying dependence. The key mixing coefficients allow us to precisely quantify that degree of dependence between events. At different positions within the sequence, they tell us how much memory the system has.
So if the emixing coefficients are small, it means the past has very little influence on the present.
Exactly. And the matrix is essentially a way to organize all those emixing coefficients into a structured format. It captures the overall pattern of dependencies within the sequence. Think of it like a map of how events influence each other over time.
Okay, so we've quantified the dependencies, but how does that help us apply the concentration inequality?
Here's the key insight. They prove that the norm of this matrix, a way to measure its overall size, is bounded. This means even though we have all these dependencies, they're not running wild. They're contained within some finite limit.
So it's like saying the ripples in our pond might be complex, but they eventually die down.
A great way to put it. And this boundedness of the matrix is crucial for applying the concentration inequality.
Now, the paper also introduces this idea of a C-Lifshitz function. What role does that play in this mathematical puzzle?
A C-Lifshitz function is essentially a function that doesn't change too abruptly. Its rate of change is controlled by a set of coefficients, denoted by C. Imagine a smooth rolling hill as opposed to a jagged mountain range.
So it's about having some level of smoothness or predictability in how the function behaves.
Precisely. And the function they're interested in, the probability of observing a certain number of word occurrences within a sequence, actually satisfies this C-Lifshitz property.
So even though the individual probabilities might jump around a bit, the overall function describing those probabilities is well behaved.
Exactly. And the C-Lifshitz property, combined with the boundedness of the matrix, allows them to apply the concentration inequality.
This is starting to sound like the grand finale of a mathematical symphony, with all these instruments coming together in harmony.
It truly is. They combine the Azuma-Hufting coefficients, the mixing coefficients, the matrix, and the C-Lifshitz property. to prove a powerful concentration inequality. This inequality tells us that for almost every sequence generated by these systems, the actual probability of observing a certain number of word occurrences will be very close to the average probability we'd expect from the annealed result.
So they've bridged the gap between average behavior and the behavior of individual sequences.
Precisely. And with this concentration inequality in hand, they finally clinch the quenched result. They show that for almost every individual sequence, the distribution of word counts does indeed converge to a Poisson distribution as the word length increases.
Wow, what a journey. We went from basic concepts of probability and randomness to sophisticated tools like matrices and concentration inequalities, and it all came together to prove this profound result about the predictability of randomness.
It's a testament to the power of mathematics to reveal hidden patterns and order within seemingly chaotic systems.
So what's the takeaway for our listeners, the big so what of all this?
Well, this result tells us that even in systems that appear random, there are often underlying structures and patterns waiting to be discovered. And understanding these patterns can unlock deeper insights into a wide range of phenomena, from the behavior of algorithms to the distribution of galaxies in the universe.
It's a reminder that there's always more to learn, more to explore, and that even in the face of complexity, mathematics can provide a path towards understanding. Thanks for joining us on this deep dive.
Until next time, keep exploring the fascinating world of mathematics.
All right, folks, ready to dive into something pretty abstract today.
Always up for a challenge.
I know you guys are all familiar with the Poisson distribution, but have you ever heard of Poisson genericity?
Sounds intriguing.
Yeah, it's this concept, right, that looks at how often patterns, in this case, blocks of symbols, appear in sequences.
Okay.
And if their distribution kind of mimics the randomness you'd see in a Poisson process.
So it's like we're trying to find a specific fingerprint of randomness.
Exactly. And what's wild is how this idea, it pops up in fields you might not expect at first glance, like dynamical systems.
Oh, interesting.
And number theory. It's like we're uncovering these hidden connections between the structure of number sequences and the way certain systems evolve over time.
So how are we going to untangle all of this?
Well, today we're going to be dissecting a paper, really getting into the nitty-gritty. It's called Poisson Genericity in Numeration Systems with Exponentially Mixing Probabilities.
That's a mouthful.
It is. But trust me, we're going to make it crystal clear.
Sounds good. Let's jump in.
All right, so page 1, they jump right into defining Poisson genericity. But in the context of these symbol sequences, it's all about analyzing how these blocks of symbols are distributed, almost like we're mapping out like constellations in a mathematical universe.
I like that analogy.
Yeah, and the tool they use for this mapping is the point process. It basically acts as a lens, like a mathematical lens, to zoom in on how these symbol blocks are distributed.
Can you give me an example?
Sure, so think about continued fractions. The paper actually proves that almost all real numbers, when expressed as continued fractions, have this Poisson-like randomness in their structure.
So it's not just theoretical, it has real applications.
Right. And it's even cooler when you consider the history. I mean, Dublin, way back in 1940, was already poking around with Poisson laws and continued fractions. So this paper really builds on that foundation.
It's amazing how ideas from decades ago can still spark new discoveries.
Absolutely. Okay, turning to page 2, we hit these crucial conditions that are like essential for their main theorem: exponential mixing and invariance.
Those sound pretty technical.
They are. But basically, they guarantee a certain level of well-behavedness in the sequences they're studying.
Well-behavedness?
Yeah, think of it this way. If you're analyzing coin flips and the coin's fair, you expect a certain balance of heads and tails over time, right?
Right.
So exponential mixing and invariance are like a way to formalize this idea of balance, but in a more general setting.
So where do these conditions actually show up, like in real examples?
Great question. Consider dynamical systems, like beta shifts or certain maps of the interval. Those systems have rules about how they transition from one state to the next, and under the right circumstances, those transitions can exhibit this exponential mixing and invariance we're talking about.
So it's like there's a predictability within the randomness.
Exactly. Okay, now on pages 3 through 6, they dive into the proof of their main theorem, and they break it down into 2 parts, like a 2-act play. The annealed result and the quenched result.
Okay, so 2x. What's the difference?
Well, the annealed result focuses on the average behavior of these sequences. And then the quenched result, it zooms in on individual sequences. Like it's showing that this Poisson-like randomness is true not just on average, but actually for almost all sequences.
So they're really building up the argument here.
They are. And for the annealed result, they use this really cool method called the Chenstein method.
I've heard of that one.
Yeah, it's this powerful technique for like approximating how closely a sequence of events resembles a Poisson process. And within this part of the proof, lemma 4 is a key stepping stone.
What does lemma 4 do?
Well, it basically establishes that on average, the behavior of these sequences really does align with the Poisson distribution. It's like laying the groundwork for everything that comes after.
It sounds like we're about to get into the really technical stuff.
We are. But before we do, maybe it's a good time to step back and think about why all of this matters. You know, why should we even care about Poisson genericity?
I'm all ears.
Well, it's not just about, abstract mathematical beauty. It actually has far-reaching implications. I mean, it helps us understand these seemingly random patterns in all sorts of fields, like the distribution of prime numbers, or even the behavior of complex systems in physics and computer science.
Wow, so it's like we're uncovering a hidden language that speaks to the fundamental structure of things.
Exactly. And as we dig deeper into this paper, we'll see how these abstract mathematical concepts really can shed light on the patterns and the randomness that permeate our world. So, ready for part 2 of this mathematical adventure?
Absolutely. Lead the way.
All right, let's do it.
Welcome back. Diving into the details of this paper has been quite a ride.
I know, right? Like they've really gone above and beyond in laying out the annealed result.
It's impressive the level of rigor they've put into it, wouldn't you say? So picking up where we left off, on page 3, they introduce a bunch of definitions that are key to analyzing the mixing properties of the measure, the one they denote as...
Right, and they define the contraction ratio, represented by the Greek letter.
Yes. It essentially quantifies how fast the influence of past events, diminishes as we move further along the sequence.
So a smaller row means things kind of like decay more rapidly.
Exactly. It makes analyzing the sequence from a probabilistic viewpoint much easier.
It's like if you were analyzing a chain reaction, and every event triggers the next, but with like less and less intensity each time.
Precisely. They also define the bounded distortion constant denoted by R.
Oh, right. R. What does that one do again?
Well, it ensures that the probabilities of certain patterns, occurring, they stay within reasonable bounds, even when you're dealing with these potentially infinite sequences.
So it's like a safeguard, making sure those probabilities don't go haywire.
Exactly. With those definitions in place, they move on to lemma 1 on page 4. And let me tell you, it's a pretty substantial one.
It does look a bit intimidating at first glance.
It is, but they break it down nicely into 3 main points, each focused on calculating, expectations and variances for our point process.
The WKS thing.
Yes, precisely. And the first point, it establishes a formula for the expected value of MWKS, showing that it's basically the same as the measure of the set S plus a tiny error term that shrinks exponentially as Meki grows.
So that's where the contraction ratio comes in again, keeping those error terms in check.
Precisely. Then, point 2, it tackles the expected value of the square of MWKS. A bit more complex, but it all boils down to a formula involving the set S, and again, those diminishing error terms.
And then point 3 uses the previous 2 points to get a formula for the variance of MWKS.
Yeah.
Setting us up nicely for that Chenstein method later on.
Yes, lemma 1 really lays a lot of groundwork. It's quite impressive.
Definitely. Okay, so moving on to page 5, we hit lemma 2. And this one seems to shift gears a bit from looking at individual words to the entire the whole collection of words in our alphabet.
Right. If lemma 1 was like a microscope, lemma 2 is like a wide-angle lens. It focuses on calculating the expected value of the entire point process, MKS, across all the different words.
And the result they get is pretty elegant, right?
It is. The expected value of MKS turns out to be essentially equal to the measure of the set S, with an error term that, again, shrinks exponentially as k increases.
So it's confirming that, on average, our point process is behaving the way we anticipate.
Exactly. It reinforces the idea that even though individual sequences might have some quirks, the overall behavior tends towards a predictable pattern.
It's like watching a flock of birds. Each bird might take a slightly different path, but the flock as a whole, it moves in a cohesive direction.
An excellent analogy.
I'm really starting to appreciate how these lemmas, they build on each other. It's like they're constructing this intricate mathematical structure piece by piece.
Absolutely. But before we jump to page 6, maybe we should pause for a second and think about the bigger picture.
Yeah, good point. We've been deep in the weeds here. What does all of this tell us about the world beyond these abstract mathematical concepts?
That's the beauty of it, right? Exploring Poisson genericity, it's not just an intellectual exercise. It actually reveals this fundamental aspect of randomness that pops up everywhere. From number theory to analyzing complex systems, it's like we're uncovering a hidden code that governs the distribution of patterns in all sorts of phenomena.
So it's like the same mathematical language can be used to describe things like the arrangement of stars or the stock market or even the patterns in a snowflake.
Precisely. And as we continue with this paper, we'll see how these seemingly abstract ideas have these profound implications for understanding the world around us.
I love that. All right, with that broader perspective in mind, I'm ready to tackle page 6, ready to dive into the intricate world of the Chenstein method.
Let's do it.
Okay, so we're back, and we're finally at the home stretch of our Poisson genericity deep dive.
Yeah, we've covered a lot of ground. We've unpacked the annealed result, and now it's time to really grapple with that quenched result.
It is. It is. And to pull this off, the authors bring out these really powerful tools, concentration inequalities.
Right, they're like mathematical guarantees, assuring us that the values we're looking at, they stay clustered around their expected values.
So it's like, even in the realm of individual sequences, there's still a predictable order there under the surface.
Exactly. And on page 7, they outline how they're going to prove this quenched result, which involves adapting the martingale difference method.
Ah, yes, the martingale difference method. Yeah. It's a way to break down a complex random process into like smaller, more manageable chunks.
Precisely. But before they can really use this method, they need a few more theoretical pieces in place.
And that's where Proposition 4 comes in.
It is. Proposition 4 gives an upper bound for these things called Azuma-Hufting coefficients.
Right. Those coefficients, they measure how much each individual event can influence the overall outcome of a random process, if I remember correctly.
You got it. They're like a gauge, showing us how much power each event has to sway the final result. And by bounding these coefficients, we gain more control over the overall variability of the process.
So it's like setting limits on how much each player can influence the game.
Exactly. And building on that, Proposition 5 takes those bounded coefficients and uses them to derive this really powerful concentration inequality.
And this inequality is like the core of the quenched result, right? It's what gives us that precise mathematical statement about how those individual sequences stay close to their average behavior.
Absolutely. And what's even cooler is that they extend this inequality to handle infinitely many variables in Proposition 6.
Which is crucial for dealing with those infinite sequences we're interested in.
Right. Now we come to lemma 9 on page 11. This lemma applies all those concentration inequalities we've worked so hard for to our specific problem.
So it's showing that for almost all sequences, the things we care about, like, the expected number of pattern occurrences, they stay pretty close to their averages.
Exactly. It's the moment of truth for those concentration inequalities, and they pass with flying colors.
Okay, and then finally on page 12, we hit the grand finale, lemma 10.
This is it, the culmination of everything. This lemma takes all those pieces, those lemmas and propositions and inequalities, and weaves them together to prove the quenched result.
It's really remarkable how they bring it all together. So to sum up, for almost all individual sequences, their behavior really does converge to a Poisson process.
Exactly. We've gone through a lot, but I think the key takeaway here is that Poisson genericity, it's not just some abstract idea. It's actually a powerful tool to understand how patterns are distributed in sequences.
And not just on average, but for almost every single sequence.
Exactly. It really highlights the beauty and the universality of math, how a concept like the Poisson distribution can have such a big impact on, understanding randomness in all these different fields.
It's a good reminder that there are these hidden connections all around us just waiting to be discovered, and math gives us the tools to find them.
Well said.
So next time you see a random pattern, remember there might be some beautiful math hiding beneath the surface. And for those who want to learn more, I highly recommend checking out the full paper, really dive into the fascinating world of Poisson genericity. Well, that's a wrap for our deep dive today. We hope you enjoyed this journey into the elegance of math and its connections to the world around us. Until next time, keep exploring, keep asking questions, and stay curious. Welcome back to the deep dive, ready to plunge headfirst into another complex topic.
Always exciting to see where we end up.
Today, we're going deep into Poisson genericity.
Yeah.
Specifically, its applications in numeration systems.
It's an area ripe with possibilities, especially when you consider how random events occur in systems governed by rules.
Exactly.
Yeah.
Our main source today is Poisson genericity in numeration systems with exponentially mixing probabilities.
Published just this week.
It's dense, but that's why we're here, to unpack it.
Absolutely.
So you ready to dive in?
Let's do it.
Okay. For our listeners who might not be as familiar, how would you explain Poisson genericity in a way that's accurate but also engaging?
Well, it's all about the distribution of events. Like imagine flipping a coin.
Yeah.
Each toss is random. But over many tosses, we expect a certain distribution of heads and tails. Poisson genericity suggests that certain events occur randomly, even within systems with underlying structure.
So it's not just that individual events are random, but also the randomness of sequences of events.
Exactly. Now apply that to numeration systems. Think of the decimal expansion of a number.
Okay.
Poisson genericity here implies that the frequency of certain digit blocks, as those blocks lengthen, follows a Poisson distribution.
So if we analyzed a long string of digits in pi, the likelihood of finding a specific 5-digit sequence should follow a pattern, even though pi itself is irrational and non-repeating.
Exactly. It's about understanding the probability of these sequences, even in the world of numbers.
That makes this research so interesting. But why should we care about Poisson genericity in these numeration systems? Why is this research significant?
Well, firstly, this paper expands on previous research, which mainly focused on integer-based systems.
Okay.
This one generalizes the concept to any numeration system fulfilling specific conditions.
Including continued fractions.
Yes, that's a significant leap.
So expanding the scope of this concept.
Yeah.
Exciting from a mathematical point of view.
Exactly, but it's more than that. The real-world implications are what's really interesting. Imagine being able to model random occurrences in complex systems. This is important in cryptography, where randomness is key. But also data analysis, where understanding noise is crucial, even in natural phenomena with random patterns.
So we've established that this is important research. But how did they go about proving their results? What were their strategies?
The proof has two main parts: the annealed result and the quenched result.
Okay.
The annealed result focuses on the average behavior of the system.
Okay.
They use the Chern-Stein method to show that the frequency of digit blocks converges to a Poisson distribution as the block length increases.
So like a probabilistic baseline?
Yes.
Yeah.
Like if you examine random numbers and look at their representations, the distribution of those digit blocks fits a Poisson pattern.
Okay.
The next challenge is to show that this average behavior isn't just a coincidence, but that it holds true for individual numbers.
Not just the aggregate.
Right. That's where the quenched result comes in.
Interesting. How do they make that connection?
They use concentration inequalities. These demonstrate that what's true on average tends to be true for almost all individual cases. Very few exceptions.
It's a property of the system.
Right.
So we're going to dive deeper into this in the next part.
Yeah.
But can you give us a sense of what makes these techniques so effective?
Well, the elegance is in how they tie different concepts together. One crucial one is exponentially mixing.
Okay.
It describes how quickly the dependence between events decreases as you look further apart.
So if you know the first digit of a number, it doesn't tell you much about the 100th digit.
Exactly. And this ties in with the invariant measure, which ensures that the probability of observing a specific sequence is consistent no matter where you start.
So a uniform probability across the expansion.
Exactly. Then they introduce the contraction ratio.
Okay.
Think of it as a measure of how quickly the information from a few digits becomes less relevant as you consider longer sequences.
The further you go, the less those initial digits matter.
Precisely. They show that systems with an exponentially mixing invariant measure always have a contraction ratio less than 1.
Setting the stage for their proof.
Exactly. They then analyze the moments of a certain random variable, looking at the average and spread of how often a digit block appears.
Okay.
They show these moments match a Poisson distribution, hinting at Poisson genericity.
Like calculating the average of how many times 123 appears in a random number.
Right. Then they introduce the Chern-Stein method, a technique for proving convergence to a Poisson distribution.
Okay.
It involves comparing our random variables' moments to those of a known Poisson distribution.
Checking for similarities.
Exactly. They show that the difference between these moments decreases as the block length increases.
So the longer the sequences, the more their distribution looks like a Poisson distribution.
Right. To solidify this, they prove the total variation distance between the distributions.
Putting a number on that similarity.
Exactly. They prove that this distance shrinks to zero as the block length increases. So in the limit, as we look at longer blocks, our variable converges to a Poisson distribution.
It's all very meticulous.
It is. But remember, this is just the annealed result, showing the average behavior. We still need the quenched result to prove it for individual numbers, and that's where things get even more interesting.
I can't wait for the next part.
It really shows the power of probability theory.
We'll dive into that and the Gauss map in part 2.
See you then. Welcome back to the deep dive. Last time, we started our journey into Poisson genericity.
We talked about how it shows up in numeration systems.
Yes, and how random events, like those digit sequences, have patterns when you look at them through the Poisson distribution.
And that two-part proof.
Right. We established the annealed result,
Which showed that the average behavior of these systems, with those digit blocks, follows a Poisson distribution.
Exactly. We use tools like the Chen-Stein method and total variation distance to show that.
And that those digit blocks converge towards a Poisson distribution as they get longer. But we left off on a cliffhanger.
We did. The annealed result sets the stage, but it's not the whole story.
It's like the opening act.
Exactly. The quenched result is where it gets really interesting. It connects that average behavior to what happens with individual numbers.
Going from a general observation to specific cases.
Right. And to do this, they use concentration inequalities.
So,
They show that what's true on average is usually true for almost all the individual cases, with very few exceptions.
it's a fundamental property.
Right. Now, to use these inequalities, they introduce a few more ideas.
Okay.
One important one is a C-Lipschitz function.
I remember struggling with that term at first. Can you explain it for everyone?
It sounds complicated, but it's about how sensitive a function is to changes in its input,
Okay.
a measure of its smoothness. A function that changes a lot with small changes is highly Lipschitz.
And one that doesn't change much is less Lipschitz.
Right?
So with C Lipschitz, there's a limit to how sensitive it is.
Exactly.
Like a map where distances stay proportional no matter how much you zoom in or out, giving
Yeah.
you predictability.
Precisely. And they use this to analyze a function that measures how often digit blocks appear. They show it's C-Lipschitz, meaning its sensitivity is limited. So even if you change a few digits, the overall frequency of those blocks doesn't change drastically.
A built-in stability.
Exactly. Another key idea is Zuma-Hofting coefficients.
Okay.
These measure the dependence between events in the system.
Like how much one digit influences the probability of another.
Right. They find an upper bound for these coefficients, showing that this dependence decreases exponentially as events get further apart.
So knowing the first digit tells you very little about the 100th digit.
Exactly. With all of this in place, they use the Zuma-Hofting inequality.
Okay.
This says that for functions with bounded sensitivity and that decaying dependence, the chance of big deviations from the average is really small.
So deviations are unlikely, and even more so as things get further apart.
Right. And they apply this to the function we talked about earlier,
Oh.
showing that the probability of the frequency being far from the average is tiny. And this probability gets smaller as the block length increases.
The longer the sequence, the less likely it is to deviate.
Exactly. This is key because it shows that for almost all individual numbers, the frequency of digit blocks will be close to that average from the annealed result.
We're moving from the general to the specific.
Right. They take it even further, using the Borel-Cantelli lemma.
Okay.
This lemma says that if the sum of probabilities of events is finite, they won't happen infinitely often. Like if you buy a lottery ticket every week.
You might win sometimes, but not every week forever.
Exactly. So they use this to show that those frequencies won't deviate from the average infinitely often.
Eliminating the outliers.
Right. And this leads to the conclusion of the quenched result.
Okay.
They prove that for almost all real numbers, the frequency of digit blocks converges to a Poisson distribution as the block length increases, proving Poisson genericity.
Quite a journey.
It is. From random events to how randomness works in these structured systems, it shows the power of math.
And they did this for lots of numeration systems, even those with infinite memory like continued fractions.
Yes, they've really expanded our understanding of these systems.
It's a big step forward. And it's not just the results themselves, but the new techniques they introduced.
Right. The contraction ratio, the C-Lipschitz property, Azuma-Hufting coefficients. These can be used for lots of other math problems.
Opening up new areas of research.
Exactly. And speaking of that, the paper hints at something else. They focused on numeration systems. But what about other mathematical structures, like graphs or topology?
Good Poisson genericity work there, too.
Yeah, that's the exciting part. This research leads to so many new questions.
We've only just scratched the surface.
Exactly. There's a lot more to explore. That's the beauty of math.
Well, they do give a concrete example to show how this all works.
Yes, the Gauss map.
A real-world test for their ideas. Let's explore that in part 3.
It's a great way to see everything come together.
Welcome back to the deep dive. We've spent the last 2 parts really digging into Poisson genericity.
It's exploring how it plays out in numeration systems.
We've gone from the basics to real-world uses and even those complex mathematical proofs.
And how it appears in so many different numeration systems.
It's been quite a journey through abstract math, but I think we have a better grasp now of how randomness shows up in systems with their own rules.
Definitely. And to wrap up this deep dive, let's think about the bigger picture of this research.
Okay.
What's really important is not just the results, but the new techniques and ways of looking at things that it brings.
Right. It's not just saying, hey, these systems have Poisson genericity. It's about creating new tools that help us understand randomness in math.
Exactly. They've given us a new lens for these systems.
And the ideas they introduce, like the contraction ratio, C-Lipschitz property, Azuma-Hufting coefficients, those can be used beyond this problem.
It's like opening a door to a whole new set of questions.
Like a launch pad for new research.
Exactly. And that's what's so exciting. It's not the end, it's a beginning. There's so much more to discover about randomness and structure in math.
The paper does hint at that broader application. They focused on numeration systems. But could you use these ideas for other mathematical structures, like graphs or topology?
You've hit the nail on the head. That's what's so great about this research. It makes you ask new questions. It's like a seed that can grow into something much bigger.
Makes you wonder what else is out there.
There are lots of applications and connections waiting to be explored.
We've only scratched the surface.
Exactly. That's the allure of math. Always evolving and interconnected. Who knows what we'll discover next in this interplay between randomness and structure?
Well, on that note, I think it's time to come up for air from our deep dive into Poisson genericity.
It's been a challenging but rewarding journey.
I hope you, our listeners, found it as insightful as we did.
We tried to break down some really complex ideas and make them engaging.
If there's one thing to take away, it's that even in the most structured systems, there's often an element of randomness underneath it all.
Something to think about.
As always, keep exploring these ideas, keep learning.
Who knows, maybe you'll discover the next big application of Poisson genericity.
And be sure to subscribe to The Deep Dive for more explorations into the world of knowledge.
Until next time.
Welcome back to The Deep Dive. Today we're going deep into Poisson genericity.
Sounds good.
In numeration systems.
All right.
Kind of the bread and butter for us math nerds.
Absolutely.
We're going to be looking at a paper that extends this concept beyond our usual integer-based systems.
Right. Yeah.
It's a fascinating paper.
It is.
It's definitely a mental workup.
That's one.
But it's worth it.
It is.
Absolutely.
What's so interesting about this paper?
What's really cool about this is that it broadens the applicability of Poisson genericity to systems with exponentially mixing probability measures. It's a big step forward. We're moving beyond simple sequences where each symbol is independent.
Right. So we're talking about systems where
Yeah.
the probability of seeing a specific symbol depends on what came before it.
Exactly.
That adds a whole nother layer of complexity, wouldn't you say?
It certainly does.
Yeah.
And you know what makes this paper really special is that it manages to prove that almost all real numbers, when you express them as continued fractions, actually exhibit Poisson generic behavior.
Okay.
This is a major development. Continued fractions are really fundamental to number theory.
Yeah.
And they have these deep connections to all different areas of mathematics.
Okay, so let's unpack this a little bit for our listener.
Sure.
Why is this breakthrough with continued fractions?
Continued fractions, they provide a unique way to represent real numbers.
Okay.
Unlike decimal representations, which can be kind of messy and sometimes ambiguous, Continued fractions are very clean. They're unambiguous.
Okay.
And they're very closely tied to concepts like Diophantine approximation, which deals with finding rational approximations to irrational numbers.
Yeah. So when we understand their Poisson genericity, it really opens up new avenues for exploring these fascinating areas of mathematics.
So this paper isn't just about
Right.
proving some abstract mathematical concept.
Exactly.
It has the potential to give us more insight into how real numbers are structured and how they relate to each other.
Absolutely.
Okay.
So to get into the meat of the proof, we need to understand two key parts: the annealed and the quenched results.
Okay.
Imagine you're analyzing a complex system with many possible states. The annealed result looks at what happens on average across all of those states.
Okay.
It's kind of like a big picture view of the system's behavior.
Quenched result.
Yeah. The quenched result focuses on what happens with almost every individual state, not just the average.
So that's where we zoom in.
Exactly.
Okay.
It's like going from a panoramic shot to a close-up. This paper really brilliantly demonstrates that even though individual sequences can vary, they still kind of conform to a Poisson distribution with remarkable consistency.
Okay, so now this relies on some pretty sophisticated math.
It does.
Can you give us a high-level overview of how these tools work in this?
Sure. A very powerful concept called concentration inequalities. Imagine flipping a coin 1,000 times. You'd expect, roughly 500 heads, 500 tails.
Right.
What are the chances of getting, say, 600 heads?
Yeah.
Concentration inequalities help us to calculate these probabilities, and they determine how likely it is for a random variable to deviate significantly from its expected value.
So these inequalities give us a way to measure how much individual outcomes can vary from the average. How do they apply to the specific context of Poisson genericity?
Well, that's really where the ingenuity of the paper lies. This paper leverages a very specific type of concentration inequality, the Azuma-Hafting inequality. And they use this to analyze the word counting process within sequences.
Okay.
Remember, we're interested in how often specific patterns or words appear within these sequences.
Yeah.
The Azuma-Hafting inequality allows us to understand how much the count of these words can fluctuate from sequence to sequence.
Okay. I'm starting to see how the pieces fit together here.
Good.
So we're using this inequality to establish that the distribution of word occurrences in individual sequences, even though they can vary, still generally adheres to a Poisson distribution.
Precisely.
Now,
to make all this work,
Yeah.
the paper lays out two very crucial conditions that the system must satisfy.
Okay.
The first is an invariant probability measure. This means that the underlying probabilities governing the system remain stable, regardless of where you are in the sequence.
Okay.
It's like having a fair coin.
Yeah.
The probability of getting heads or tails doesn't change whether you're on your first flip or your 100th.
Right.
Okay.
And the second condition?
The second condition is what's known as an exponentially mixing probability measure.
Okay.
This one's a bit more technical, but essentially it ensures that events that are far apart in a sequence eventually become almost independent of each other.
Okay.
Think of it like ripples in a pond.
Okay.
They spread outward, their influence on each other diminishes until they become essentially separate events.
Okay, so we need these two conditions,
Exactly.
invariance and mixing,
That's right.
to guarantee that our word counting process is going to show Poisson generic behavior.
Yes.
Okay, now before we dive deeper into the proof itself, can you talk a little bit more about what these words are and how they factor into the analysis?
Sure. In this context, a word is just a specific sequence of symbols from our alphabet. It could be a sequence of binary digits like 0, 1, 1.
Right.
Or it could be a sequence of letters, math. The length of the word is simply the number of symbols it contains. And what we're really interested in is how often these words appear within the larger sequences generated by our system.
Okay, so how do we actually count these words? Is it as simple as it sounds, or are there complexities involved?
It's a little more nuanced than a simple count.
Okay.
We have to consider not just the total number of times a word appears, but also the positions where it appears within the sequence.
Okay.
Think of it like analyzing a piece of music. You're not just interested in how many times a particular note is played, but where it occurs within the melody and how it contributes to the overall structure.
So the position of a word in a sequence matters.
Exactly.
Just as much as its frequency.
That's right.
How do we incorporate that positional information into our analysis of Poisson genericity?
That's where the concept of an integer-valued random measure comes in. It's a mathematical tool that allows us to capture both the count and the positions of words within a sequence. Think of it like having a really detailed map that not only shows you where all the cities are located, but also tells you the population of each city.
So this measure gives us a
Right.
much richer,
Exactly.
richer pictures.
How
Yeah.
words are distributed within a sequence.
Precisely. And this detailed information is crucial for establishing what we call the annealed result,
Right.
which is the first part of the proof.
Okay.
This is where we analyze the average behavior of word occurrences
Right.
across all possible sequences that are generated by the system.
Okay.
We use this integer-valued random measure
Yeah.
along with some other powerful tools from probability theory, like the Chenstein method,
Okay.
to demonstrate that the average distribution of words
Yeah.
converges to a Poisson distribution
Okay.
as the length of the words increases.
Okay. So before we go any further.
Can you talk a little bit more about why the Chenstein method
Yes.
is so important in this context? What does it allow us to do?
The Chenstein method is a really powerful technique for approximating the distribution of a sum of dependent random variables.
Okay.
In our case, the occurrences of words within a sequence are not necessarily independent events.
All right.
The appearance of one word might influence the probability of another word appearing nearby.
Right.
The Chenstein method allows us to handle these dependencies
Okay.
and still show that the overall distribution converges to a Poisson distribution.
So it's incredibly useful
Very useful.
for bridging the gap between the complexities
Absolutely.
of these real-world sequences and this elegant simplicity of the Poisson distribution.
It really is.
We've covered a lot already.
Yes, we have.
Maybe it's time to take a quick break, and then we'll come back and dive deeper into this annealed result.
Sounds good.
All right.
I'll
See you back in a few minutes.
See you then. All right, so let's dig a little bit deeper into this annealed result. You know, this part of the proof focuses on what's happening on average across all the possible sequences.
The big picture.
Exactly. And remember, we talked about this integer-valued random measure.
Yeah.
So how does that actually work in this analysis?
Yeah.
Okay, so let's call this measure MKX. W,
Okay.
where X represents our sequence and W represents the specific word that we're looking at,
Right.
which has a length of K.
Okay.
So this measure basically is counting up how many times that word W appears in the sequence X.
Okay.
But it's not just a simple count.
So there's more to it
There's more to it.
than just tallying up the appearances.
Exactly. It also takes into account the positions where those occurrences happen.
Right. So it's not just about how many times you see it, but where you see it.
Precisely.
It's like knowing that a city has 1 million people
Right.
versus knowing
Yeah.
where in this city
Yeah.
those 1 million people actually live.
Perfect analogy.
Yeah.
And this level of detail is super important for proving that this whole thing converges to a Poisson distribution.
Okay, so how does this
Right.
this integer-valued random measure help us prove that?
Well, the paper has a bunch of these key lemmas that build up to the main result.
Okay.
And one of these lemmas gives us an upper bound
Okay.
for the expected value of our counter,
Okay.
MKX, W.
Mm-hmm.
And this bound basically says, on average, the number of times a word appears is roughly proportional to the length of the sequence.
Okay.
Which makes sense, right?
Yeah, a longer sequence should have more opportunities for a word to pop up.
Exactly.
Yeah.
Now, another really important lemma
Okay.
connects the expected value of our counter to the
Okay.
Poisson distribution.
Right.
So it shows that if we take a function
Okay.
and apply it to our counter,
Okay.
say HMKXW,
Okay.
we can approximate that expected value using the average value of that same function
Okay.
under a Poisson distribution.
So we're linking
Yeah.
our word counting process
Exactly.
to the Poisson distribution using this lemma.
We are, and to really solidify that connection, we use the Chenstein method.
Ah, the Chenstein method.
Yes.
You mentioned this earlier.
It's a really powerful tool.
It sounds like this method is really important.
It is. It helps us bound the difference between the distribution of our word counter
Okay.
and an actual Poisson distribution.
So it's doing a lot of heavy lifting in this proof.
It is.
Okay.
It's super useful when you're dealing with dependent random variables.
Right.
And remember, the occurrences of words in a sequence aren't always independent.
Right, because one word appearing could affect whether another word appears later.
Exactly. So it's not like flipping a coin.
Right. Each flip is totally independent.
Exactly. And we need a way to account for that, and that's where Chenstein comes in.
Yeah.
And what's cool is that even with those dependencies, The Chenstein method lets us show that it still converges to a Poisson distribution as the words get longer.
So even though we add in complexity
Yeah,
by looking at these dependencies,
right.
the overall pattern still holds.
That's right.
That's pretty fascinating.
It is.
Okay.
Now, the paper goes on to extend this analysis to this thing called the product space
Okay.
of sequences and words,
Well, all right.
which they denote by AA.
Okay.
And this is a little more abstract, but essentially it allows us to look at all the possible combinations of sequences and words.
So we're moving beyond just looking at individual sequences.
Right.
And now we're looking at
We're looking at the whole landscape
the whole land.
of all possible sequences and the words that are in them.
Okay.
And by working in this product space, the paper establishes the annealed result,
Right.
which is that the expected value of our word counter
Okay.
in this space
Yeah.
also converges to the expected value of a Poisson distribution as the word length increases.
Okay.
So that's a pretty powerful result.
It is.
And it sets us up really well for this quenched result,
Right.
which is where we zoom in on individual sequences.
Right.
But before we move on, can you talk a little bit more about how the Chenstein method is actually applied here?
Yeah, it feels a little bit like a black box right now.
Sure. So the core idea is to approximate the distribution of our word counter, MKX, of
Okay.
UX,
Right.
by a Poisson distribution that has the same expected value.
Okay.
And to do that, we need to bound the distance between the two distributions.
Right. So how different are they really?
Exactly. And we measure that using a metric called the total variation distance.
Okay.
The smaller the distance, the closer our word counter is to a true Poisson distribution.
So we're trying to figure out how much does our counter deviate from a perfect Poisson scenario?
Precisely. And Chenstein gives us a way to bound that total variation distance using something called coupling.
Okay.
And that's where you basically construct two random variables,
Okay.
one representing our counter and the other representing a true Poisson variable.
Okay.
And you try to make them as close as possible.
So it's like creating a parallel universe
Yeah, you can think of it that way.
where our word counter is behaving like a Poisson variable.
Exactly. And then you analyze the differences
Right.
between those two.
Yeah.
And that gives you an upper bound on the total variation distance,
Okay.
which then lets you show that the distribution converges to a Poisson distribution.
So we're using this parallel universe
Yeah,
to get some insight into how our counter behaves in the real world.
that's a great way to put it.
Yeah.
And what's really neat is that even though it uses these kind of abstract math ideas,
Mm-hmm.
it lets us make concrete statements about how these sequences actually behave.
It's a good reminder that even
Yeah.
the most abstract mathematical ideas can really help us understand the world around us.
Absolutely.
Yeah.
Okay, so the annealed result gives us this average behavior.
Mhm.
But the really cool stuff happens when we go to the quenched result,
Right.
which looks at individual sequences.
Yeah, and how they behave.
Exactly.
Right.
And shows that they also exhibit Poisson generic behavior.
Okay.
But we'll save that for next time.
All right, so welcome back to the final part
Yeah.
of our deep dive.
Okay.
We spent the last two parts
Yeah.
laying the foundation, exploring the annealed result,
Right.
which focuses on that average behavior.
Right.
And now we get to the really cool stuff.
The fun part.
The quenched result, where we zoom in on
Sure.
individual
Yeah.
sequences.
Yep.
And it's amazing to me to think that
It
with all the variability that we could see in those sequences, that they still kind of follow this
Yeah.
Poisson distribution.
It's remarkable.
Yeah, so what tools let us?
Well, a big one
Yeah.
is concentration inequalities.
Okay.
And these inequalities give us a way to measure
Yeah.
how much a random variable can deviate from its expected value.
So in our case, that would be how much the actual count
Yeah,
of a specific word in a sequence
exactly.
might differ from the average that we would expect.
Right. And the paper uses this specific type
Yeah.
of concentration inequality called the Azuma-Hufting inequality. And this one's really well suited
Yeah.
for when you have a bunch of random variables in a sequence.
Right.
And the value of each one depends on the ones that came before it.
So perfect for our situation,
Exactly.
where one word can affect
Yep.
another word
Agreed.
appearing later on.
Now, applying the Azuma-Hufting inequality
Yeah.
to this is not easy.
Right.
The researchers had to really work with it to make it handle systems with infinite memory.
Okay, so what does that mean?
Well, it means that infinite memory, the probability of each symbol
Yeah.
depends on an infinite number of preceding symbols.
Oh, wow.
So that's tough mathematically.
Yeah, so like trying to predict the next word
Yeah.
that someone's going to say
It's like
based on every word they've ever said in their life.
That's exactly it.
Wow.
That's a lot of information.
Yeah, that's incredible.
But the researchers were able to handle that.
Okay, good.
They came up with this really powerful concentration inequality. That applies to functions depending on a countably infinite number of variables.
Wow. So they tamed the wild beast
They
of
did.
infinite memory with this inequality.
They did.
That's pretty amazing.
It is, and this has some really big implications.
Okay.
It lets us show that for almost every single sequence generated by this type of system,
Okay.
the distribution of word occurrences lines up really well with a Poisson distribution.
So it's not just on average anymore.
Exactly.
Almost every sequence.
Almost every sequence follows this pattern.
Wow.
And to kind of make that even stronger,
Okay.
the paper goes on to prove another lemma
Okay.
that puts an upper bound on the probability
Okay.
that the actual word count
Mm-hmm.
deviates from its expected value by a certain amount.
So this lemma tells us how unlikely it is
Exactly.
for a sequence to stray too far from that average.
That's right.
Okay, so it's like a safety net.
Yeah, like a safety net, making sure things don't get too crazy.
Right.
And this bound is really tight. So it gives us a really accurate estimate.
So we can be pretty sure
Yeah.
that most of the time these sequences are going to stick close to that Poisson behavior.
Right. And with this bound, they bring in another big tool from probability,
Okay.
Kahlenberg's theorem.
Okay.
And this theorem gives us a checklist,
Okay.
a bunch of criteria that if we meet them,
Yeah.
we can be sure that a sequence of random variables converges to a Poisson process.
Okay.
And the paper very carefully shows that everything in their system checks all those boxes.
So they went through the whole checklist
They did.
and everything checks out.
Exactly.
Yeah.
And that's how they prove the quenched result.
Wow. So we've come a long way.
We have.
We started by talking about Poisson genericity,
Yeah.
how this paper extends it to these systems with exponentially mixing probability measures.
Right.
We looked at the annealed results, which is that average behavior,
Mm.
and then we really dug into the quenched result, which is,
The individual sequences.
yeah, the fact that they all kind of conform to this.
It's all right.
Elegant
Yeah.
mathematical pattern.
Really neat.
Yeah, that's amazing.
And it's really a testament to all these powerful tools
Yeah.
that mathematicians have developed.
Concentration inequalities,
Mm-hmm.
Kahlenberg's theorem,
It's pretty amazing.
all this stuff.
Yeah, and it's really cool how they were able to adapt all these tools
Right.
to solve this problem.
Yeah, it really gives you a new appreciation
It does.
for how elegant math can be
Absolutely.
and how these seemingly abstract concepts
Yeah.
can really help us understand how the world works.
It's pretty cool.
Well, this has been a fantastic deep dive.
I agree.
Thank you for joining me.
My pleasure.
And I encourage everyone to go check out this paper and see what other insights you might uncover.
It's a good one.